Imagine you've just turned your kitchen oven on and set it to bake. You open the door and slide in a cold pan. After a few minutes of preheating, the air inside the oven reaches your target temperature. In engineering, we call an environment where the temperature remains constant over time a steady state. But the cold pan you just put inside is a different story. Its temperature is continuously climbing, changing from minute to minute as it absorbs heat from the surrounding air. When temperatures are actively changing over time, we call it transient heat conduction. A central goal in thermal engineering is predicting exactly how those transient objects will heat up, allowing us to determine exactly how hot they will be at any specific second in the future. Let's run a test. We are going to place two very different items into our hot oven, a thick cut of roast beef and a small copper ball. Looking at this diagram, the beef shows massive temperature differences. The outside is a scorching 110 degrees, but the center is a cool 40. Now, look up at the copper ball. It's highly conductive, so its internal temperature is exactly 70 degrees everywhere simultaneously. Because the metal ball heats so evenly, we don't have to map out 100 different internal zones. Engineers can treat the entire object as a single, uniform unit, using a method called lumped system analysis. Before we can use that method, we have to prove mathematically whether an object will act like the evenly heated copper ball or the unevenly heated beef. This simple equation calculates the Biot number. Think of it as a mandatory test every object must pass before we can use the simplified model. In this diagram, the Biot number is really just a ratio comparing two things. The pink arrows show how fast heat hits the outside surface. That's convection. The inner arrows represent how fast that heat can travel through the inside of the object. That's conduction. The rule is clear. If heat spreads through the inside of the object much faster than it arrives at the surface, the temperature stays uniform. Mathematically, that means getting a Biot number of less than 0.1. Our copper ball easily scores below 0.1, passing the test. The roast beef fails. We are officially cleared to use the shortcut on the ball. This exact formula is lumped system analysis, a recipe for predicting future temperatures. If you focus on the left side, this chunk looks at the starting temperature gap between the cold object and the hot oven air. Moving to the right, this new equation defines the letter B. This represents the material's unique thermal speed limit, built entirely from its physical properties, like mass and density. If we flip B upside down, we get the time constant. Like the two dials you see here, this acts as the object's personal internal stopwatch. A small time constant means the object absorbs heat rapidly, while a large one means it fills up slowly. Finally, the letter T in the exponent acts as your time input. You can plug in any future minute or hour you want. By treating the object as one uniform lump, we skip the exhausting 3D thermodynamic mapping. This recipe lets you calculate the exact state of the object at any point in the future in a matter of seconds. Look at this copper ball sitting in a 200-degree oven. Our goal is to predict its core temperature exactly 3 minutes from now. Watch what happens as we feed our known variables into the equation. We add the oven temperature, the properties of the copper, and our 3-minute time target. The math resolves instantly. The prediction? 185 degrees. If we open the oven at the 3-minute mark and check the core with a physical thermometer, it reads precisely 185 degrees. The equation didn't guess. It accurately mapped out reality using the strict physical laws that govern uniform heating. Out in the real world, aerospace and electronics engineers rely on this specific equation every day. Take a look at this split screen. Engineers could spend weeks running the supercomputer simulations on the left for every tiny component they design. Or they can pick up a pencil and solve the single equation on the right. We started by separating steady environments from transient ones. We used the Biot number to filter out uneven objects, and we applied lumped system analysis to the things that heat uniformly. Understanding these thermodynamic rules allows engineers to accurately model how a component will behave long before it ever enters a lab.